Yeah, welcome everybody also from my side. My name is Upschulte, and I'm going to talk about contour proposal networks for neuronal cell detection. A few words about me. I'm a PhD student in the Forschungszentrum Jülich, or Research Center in Jülich. And my main work deals with the segmentation and detection of microstructures in the 1 micron big brain data and similar high resolution imaging. Yeah, this is what this may look like. An example, on the left-hand side, you can see a typical input image with many cells. And on the right-hand side, you can see an example segmentation. The reason why this is difficult, if you look close enough, you might spot it. There are a lot of cells, and a few, or a lot of them actually, are clustered, so they are very close together. They're touching, and the boundaries are not always clearly visible. Also, cells, of course, are distributed in 3D. In this case, it's a 2D image, so you can have also overlapping instances. And in our case, you really want to preserve the entire morphology and get the entire cell at once. So there are several different aspects that make this a challenging task. Today, I will present you the contour proposal network, which is our choice to tackle all those problems. And I will show you how it works and hopefully give you an intuition what it actually does internally. This is an overview of the network architecture. You don't have to get everything at once. We go through the architecture bit by bit in the following slides. For now, just as an overview, on the left-hand side, you again have an input image. Then there is a backbone, CNN, so a convolutional neural network that basically computes all the features that we then use for the detection part. In the middle, you can see there is a classifier. That one basically determines if an object is present at a given location in the input image. If there is an object present, the contour regression will then produce a vector format that describes the entire object contour. This is basically what you can see here. So the entire object contour, as you can see on the right side, is described by the contour regression in vector form. After that, we basically use the classification result to extract a list of all contour representations that actually represent an object in the input image. Apply a so-called local refinement to make sure that we are as precise as possible, and finally apply a non-maximum suppression. So as I said, we will go through all the steps bit by bit. Okay, first some basics. What is a contour actually in this case? When we talk about contours, we mean actually a sequence of X, Y coordinates. On the left-hand side, you can see an example. This cell structure is described by all those contours, and this is just a tiny fraction of all those coordinates, and this is just a tiny fraction of all the coordinates that actually make up all the details of this contour. And how exactly do we represent contours in our network? Because we want finally to be able to use a convolutional neural network to predict those contours. For that, we use contour representation that makes use of the Fourier sine and cosine transform. These are the functions that you see here. They might look a bit confusing at first, but they are rather intuitive, as you hopefully will see in the next few slides. So mainly we have two functions. One allows you to sample all the X coordinates that make up a single contour. And the function below allows you to do the same for all the Y coordinates of an entire contour. And highlighted now in color are all the parameters that are predicted by a convolutional network. So deep learning allows us to predict those parameters, and the function then allows us to sample the actual coordinates. And what's nice about this is that there are only a few parameters needed to get a lot of actual contour coordinates. And it's always better to see things if you want to understand things. So this is an example. Here we sample coordinates by coordinates, and can see that the network kind of learns how to draw the outline of a cell. Luckily, what happens here sequentially, for illustration, happens in one single computational step in practice. So this is really efficient. What is also noteworthy is that these functions are derivable, so we can actually do end-to-end training with them. This is what this looks like. Another useful property is that this function ensures that the contour always starts where it ends. So by definition, it will always result in a closed contour, which is of course what we desire. When working with contour representations, there's also the question of how to limit the information that you're able to store. And this is rather intuitive in our case, using the Fourier sine and cosine transform, because we have a single hyperparameter n that we can set, and it allows, or it sets the number of values used to represent the contour. If you set it to 1, you have only 6 values that describe a single contour, and you only get an ellipse fitting. If you are working with objects or cells that are elliptic, that's fine enough. Then in our case, that's not enough. So you can increase it, for example, to n equals 3, then you are already getting a good approximation of the contour, and you can increase it further to add more detail to your network. So this is really intuitive and understandable. Then there's also always the question, can you also do, a bit off topic now, very complex shapes, complex in the sense that this is really non-convex with a lot of detail, and this is also possible given the order is high enough. Okay, if you have worked with object detection so far, maybe with bounding box regression models that basically put a rectangle around an object, then you know that misalignments can happen, especially if you're working with data sets that are rather small, and that's not uncommon in the biomedical domain. So something like this might happen. In this case, you can see the contour is too far below. There's some white space here that is deemed to be part of the cell, even though that's obviously not correct. So the question is, what can we do about this? Because we really want to be precise. In our case, we found that we can leverage the fact that we have all the XY coordinates of the contour already. So what we do is we introduce a few convolutions extra to our network and produce a 2-channel feature map. We call it the refinement tensor. So it has 2 channels, and then we can just use the XY coordinates that we already have from the contour and look at the value at the position XY. And this value, this 2-dimensional vector, we just add to our current coordinates. By doing this simple step, we allow the network to do a form of self-correction. And this is leveraging really local information. So if a contour point is landing here in the white space, the network can directly learn to correct this. This is an example of it. Again, for illustration, we go through it coordinate by coordinate, and you can see if the border is kind of correct, the network will learn to not correct anything. And once there is a divergence, which happens right now, you can see the network decides to shift the coordinates towards the proper boundary. So this is learned really efficient and also works with smaller data sets. So the combination of our 2 approaches, first the proposal, then the refinement, allows us to do really precise segmentation here. Then there's also the part called non-max suppression. This is the final step in the network. The job of this step is to select a single solution out of many proposed solutions. So you can see here an extreme example, and you can see that not all of those proposals are actually good solutions. And non-maximum suppression is supposed to pick one of them. The way it usually does it is it picks just the one with the highest classification score. The problem here is, however, that you can't rely on the classification score to actually represent the quality of your detection. And this is a very common problem in object detection because many methods use non-maximum suppression. In our case, with the contour proposal network, however, this is not as much of a problem as you will see now. Because if you think about it, if a network proposes different contours that are somewhat similar, the local refinement will then shift all the coordinates towards the proper boundary. And this refinement is done to all proposals the same way. So after refinement, all the proposals are almost identical. In this case, we have measured this with over 20,000 cells. Before refinement, you can see they are almost similar, but there are still quite significant differences. However, after the refinement, they are almost all identical. And the similarity is here measured with intersection over union among all redundant proposals. Another noteworthy point is the inference time. With the entire setup, we are able to do real-time computation. That depends, of course, on the choice of the backbone architecture. In this case, there's an example with the ResNet-50 FPN, and this gets 30 frames per second with an image size of roughly 500 by 700 pixels. Also noteworthy, the refinement step, if you repeat it 4 times, costs less than half a frame per second. So this is really fast in relative to the improvement that we get from it. With that said, this is basically all you need to know about the basic setup of a contour proposal network. If you would now like to try it yourself, you can visit our GitHub site or just pip install cell detection, and you should be good to go. If you have any questions and also maybe some different applications for this method, feel free to get in contact. I'm always eager to learn about new ideas and new applications.